Today we are going to solve three problems in relative velocity, and each of the problems we are going to do in two different frames of reference: a stationary frame and a moving frame, a ground frame and a moving frame. First problem. We are first going to solve this problem in the ground frame of reference. In the ground frame of reference, the river is flowing at 5 meters per second. And the raft is also moving at 5 meters per second along with the river. Now at time t equal to 0, a motorboat crosses it. Now the motorboat has a velocity of 12 meters per second in still water. Now when it goes downriver, the speed of the motorboat is going to be 12 plus 5, that is equal to 17 meters per second. So what the boat does, this motorboat, is travels for 100 seconds, which means it moves a distance of 17 times 100, so 1700 meters. And then it turns around and comes back. Now on its way back, it's now moving upriver, so its velocity is 12 minus the river's velocity 5, that is equal to 7 meters per second in the opposite direction. So let's say after turning around, the motorboat moves for t seconds before it meets the raft. So the motorboat has moved for 70 meters, 7 times t meters, because it has moved for t seconds. Now in the meantime, the raft has been drifting down. How far has the raft drifted down? The raft has drifted down a distance of speed 5 multiplied by the time. The time is 100 seconds plus t seconds. So 100 plus t. Now if you look at the drawing, you can see clearly and very simply the distance that the raft moves, which is 5 times 100 plus t, plus the distance that the motorboat moves on its way back, 7t, that is equal to 1700 meters. So you see, the secret to getting the correct equation is the drawing. That's why I keep telling you, in every physics problem, please make a drawing. That's the secret to solving physics problems. When you make a proper drawing, a simple drawing, the equation jumps out at you. The distance the raft moves plus the distance the motorboat moves on its way back is equal to 1700 meters. So this is 500 plus 5t plus 7t is equal to 1700. We take 500 that side, that becomes 1200. This is 12t is equal to 1200. So the time t is equal to 100 seconds. So it travels back for 100 seconds. If it travels back for 100 seconds, how far has the raft moved? The raft has moved 5 times, that's the speed, times 100 plus 100, 200 seconds. That means 1000 meters. That is the distance that the raft has moved. Now let's do the same problem in the raft frame of reference. In the raft frame of reference, the raft is not moving. The raft is moving with the river in the ground frame. River and raft have the same velocity. So in the raft frame, the river is not moving. It is still water. That means it's like a lake. The raft is simply floating in a lake. Of course, the shoreline, the trees, whatever else, the monkeys on the trees, all of those are moving backwards at 5 meters per second. But what do we care about that? As far as we are concerned, it is still water, it's a lake, the raft is at rest. So now, if a boat moves past it for 100 seconds, whatever distance it goes, for it to come back is going to take 100 seconds. So totally, as far as the raft is concerned, the motorboat makes a round trip of 200 seconds. And in 200 seconds, as seen from the ground, the raft has moved a distance of 200 times 5, that is equal to 1000 meters. So you see, this problem is so much simpler in the moving frame of the raft. Next problem. So in this problem, we have an elevator moving at a constant velocity of 6 meters per second upwards when a bulb in the ceiling of the elevator breaks loose and falls down, and it hits the floor of the elevator and breaks. The question is, how long did the bulb fall? We are first going to solve the problem in the ground frame. In the ground frame, when the bulb breaks loose, its initial velocity is 6 meters per second upwards. So let's start by taking the upward direction as positive. So it is plus 6. Now after it breaks loose, it is in free fall. So its acceleration is minus 10 meters per second squared. That's the acceleration due to gravity in the ground frame. So in the ground frame, the bulb is moving upwards when it breaks loose, but it's slowing down due to gravity. Whereas the ceiling of the elevator is not slowing down, so it's moving at a constant velocity of 6 meters per second, so it stays above the bulb, so the upward moving bulb is not going to crash into the ceiling. So when it reaches its highest point, it comes to a momentary stop and turns around and falls down. In the meantime, the floor of the elevator is moving upwards and it catches up with the bulb with a crash. Now, this upward arrow is the displacement of the elevator, and the displacement of the bulb is from the initial position of the bulb to where it meets the floor of the elevator. And so, that's the displacement of the bulb. Let's write down the equations for each of them. The displacement of the bulb, its initial velocity is 6. So if the time of travel for the bulb between when it breaks loose from the ceiling and when it hits the floor, let's say the time is t, so ut plus half acceleration of the bulb minus 10 t squared. During the same time, the displacement of the elevator is 6t. It's moving at a constant velocity. Now, if you look at this drawing, the drawing tells you what equation to write. The drawing tells you that this distance plus this distance is 4 meters. So you might be tempted to write displacement of the bulb plus the displacement of the elevator is equal to 4. You'd be making a big mistake here. That's because if you look at this drawing carefully, the displacement of the bulb is negative. Whereas the equation is this distance plus this distance is 4 meters. So what I want is the magnitude of the displacement of the bulb. Since the displacement of the bulb is negative, to get its magnitude, I multiply it by minus 1. The displacement of the elevator, on the other hand, is already positive, so it's equal to its magnitude. So this is the right equation. So let's put this down. So minus 6t, here I have minus 5t squared, that becomes plus 5t squared, plus 6t is equal to 4. 60 and minus 60 cancel, so I get 5t squared is equal to 4, and that gives me t is equal to root of 4 by 5 seconds. Now let's do the same problem in the elevator frame. In the elevator frame of reference, this 4 meter tall elevator is not moving. Around it, the elevator shaft and the building are all moving at 6 meters per second downwards. But we don't care about that. As far as we are concerned, it's a stationary elevator, and when the bulb breaks loose, its initial velocity is 0. What about its acceleration in this elevator frame? See, seen from the ground, the bulb has a downward acceleration of 10 and the floor of the elevator has an upward acceleration of 0. So from the point of view of the floor of the elevator, the bulb's acceleration is 10 meters per second squared down. This time we'll take down as positive. So displacement S is equal to plus 4, because in the elevator frame, the elevator is stationary and the bulb simply comes down by 4 meters. So S equal to 4 is equal to ut plus half a t squared. So right away you get t is equal to square root of 4 by 5 seconds. See, in the moving frame, things look so easy. Right, let's go to the next problem. So this time, the elevator has an upward acceleration of 4 meters per second squared. And when the bulb and the elevator are both moving at 8 meters per second, the bulb breaks loose. All this is what we see in the ground frame. So let's first solve the problem in the ground frame of reference. In the ground frame of reference, the acceleration of the elevator is 4 meters per second squared, and when its upward velocity is 8 meters per second, the bulb breaks loose. So the initial velocity of the bulb is 8 meters per second when it breaks loose. Again, notice that we are taking up as positive. And once it breaks loose, the acceleration of the bulb is of course minus 10 meters per second squared because it is in free fall. The elevator is now accelerating up, we'll come to that. But now when the bulb breaks loose, again it's moving upwards but slowing down due to gravity. On the other hand, the elevator is speeding up because it's accelerating upwards at 4 meters per second squared. So the ceiling will always keep above the bulb. Bulb is not going to crash into the ceiling. And the bulb reaches its highest point and turns around and then comes straight back down. The drawing is now similar to the previous drawing. The floor of the elevator in the meantime moves up to meet the bulb with a crash. This is the displacement of the elevator, the lower arrow, and the displacement of the bulb. Again, you have to draw that from its initial position to its final position. So that is the displacement of the bulb. So let's write those down. The displacement of the bulb, its initial velocity is 8. So ut, t is the time of travel of the bulb, plus half a t squared. A is minus 10, so that is minus 5 t squared. That is half a. And the displacement of the elevator, this time the elevator is accelerating. When the bulb breaks loose, its initial velocity is also 8. ut plus half, its acceleration is 4 t squared. Once again, we have to be careful. Notice that the equation we want to write down is this. The magnitude of SB plus the magnitude of SE is 4 meters. SB, as you can see, is negative, so its magnitude is minus SB. And SE, on the other hand, is already positive, so its magnitude is just SE. That is equal to 4. That's our equation. So let's do this. So the magnitude of SB is minus 8t plus 5t squared. To that you add the magnitude of SE, which is 8t plus 2t squared. The whole thing is equal to 4. So 8t and minus 8t cancel. On the left hand side we have 7t squared is equal to 4, and that gives us the time of travel for the bulb as square root of 4 by 7 seconds. Let's do the same problem now in the elevator frame. In the elevator frame, the elevator is not moving. It's stationary. So when the bulb breaks loose from the ceiling, its initial velocity is 0. And the displacement of the bulb in the stationary elevator is simply 4 meters. So displacement of the bulb is 4 meters. But what about the acceleration of the bulb? Here you got to be very careful. Notice that the bulb in the ground frame is accelerating downwards at 10 meters per second squared, and in the ground frame the floor of the elevator is accelerating up at 4 meters per second squared. So from the point of view of the floor, that is the elevator's frame, the bulb's acceleration is 14 meters per second squared downwards. So the bulb is accelerating down at 14 meters per second squared downwards in the elevator frame. Straight away, taking down as positive, S is equal to ut plus half a t squared is equal to 7t squared. So straight away you get t is equal to 4 by 7 seconds. So it is for you to determine whether you prefer this frame or the ground frame. In the ground frame, you have to make a careful drawing. In this frame, you have to be careful about the accelerations because this is an accelerating frame. But once you get a little practice, this frame will become much easier. Okay, so that's it for today. So we will meet soon in the next video. Goodbye.